In this video, I'm going to introduce the Matlab debugger. A debugger is a program that allows you to run another program under the control of the debugger and to examine the execution of that program. From now on, when I say program, I will mean the program that you want to examine, not the debugger. Most debuggers have similar features, which include the ability to stop the program at any point you choose, to examine the current values of variables, to print a traceback listing, showing the functions that have been called to get you to this point in the execution, and even to step up out of the current function to the calling function, and to examine the variables in the calling function's workspace. Matlab's debugger has all of these features. Most can be accessed using the Matlab editor as a graphical user interface, or using the command window and typing the appropriate commands. Almost all of the debugger commands begin with db, for instance, db step to take a single step in the code, db cont to continue running the code, etc. I'll introduce the features of the Matlab debugger using two examples. For the first example, I've intentionally introduced a bug in my QuadSimp program. The new version is called QuadSimp1, and it calls simp1 to implement Simpson's rule. Hopefully you remember that QuadSimp uses Richardson extrapolation together with Simpson's rule to estimate an integral to within a given tolerance. Before I look for the bug in QuadSimp1, let's see how QuadSimp, that is the correct version, works. Here I'm asking QuadSimp to integrate sine from 0 to pi over 2, and I'm asking it to do it very accurately with a tolerance of only 10 to the minus 10. I know that the exact value of the integral is 1. Here I see that the computed estimate is as accurate as it can be, meaning that the error is at the level of round-off error. Now I can watch QuadSimp execute by using the debugger. I begin by setting a breakpoint in QuadSimp.m. To be precise, this sets a breakpoint at the first executable statement in the function. Then I execute the program again. You see that Matlab automatically brings up QuadSimp-m in the Matlab editor, and that it indicates the breakpoint with a large red dot, and the current line with a green arrow. Now what can I do at this point? First, if I go to the command window, I notice that the prompt has changed. It now has a K before the prompt symbol. I can now give any Matlab command, and the command executes as if it were a command in the current window. For instance, if I type whos, I see the local variables defined in QuadSimp, not the variables that were defined when I called QuadSimp. I can look at the values of the local variables. Here I see, for instance, that f is a handle to the sine function. A, b, and tall have the expected values. It's also possible to look at the values of the variables in the editor. In fact, if I just put the cursor on a variable, Matlab displays the value of that variable. If I put the cursor on a variable that has not yet been assigned a value, then Matlab displays nothing. Now I'll show how to execute the next line of code. There are two ways to do this. The command dbstep, given in the command window, causes one line of code to be executed. In the editor, you see that the green arrow is advanced one line. Also, we see that this line of code just executed is indicated by the fact that n1 now has a value. The other way to execute one line of code is to click on the step icon in the toolbar at the top of the editor, right here. This also causes one line of code to be executed, and it's probably more convenient than typing a command in the command window. What else can I do? Well, let's take a few more steps and go to the line that calls simp within the loop. Now if I take one more step, I see that simp has executed. I2 has a value. It's 1, at least to 5 decimal places. Let's continue taking steps until I get back to the same point in the code. Matlab gives me the option of stepping into simp and observing its execution. Instead of choosing step, I click on the step in button. Or I can type db step in the command window. When I step into a function, the debugger takes me to the first line of executable code in that function. I can now step through this function and examine its variables. So for instance, here's the value of dx. Here's the value of b and of a and of n inside of this function. In this function, there's a for loop that might execute many times. I might not want to step through all of the iterations of the loop. Suppose n is at 10,000, for example. To execute the loop without stepping through each iteration, I can click on the line after the loop, on the left next to the line number, which has the effect of putting a breakpoint on that line. If I now click the Continue button, the execution will continue until the next breakpoint. I could also type dbcont in the command window. Now I'm not going to want this breakpoint again, so I'll click on the red dot to remove it before I continue. To finish the execution of simp and go to the next line of executable code in the calling function, which is quad simp in this case. I can now continue to step through quad simp, or I can click Continue. Since I don't have any more breakpoints, this causes the function to finish executing. When I return to the command window, I see that the K no longer appears before the prompt, which tells me that the debugger is no longer executing. Next, I'm going to show 3 more debugger commands that are very useful. You'll notice that the breakpoint is still set in quad simp. If you look here, the red dot is still there. So I'll execute quad simp again. Take one step, and then step into simp. If I type dbstack in the command window, I get a traceback listing that shows how I got to that point. I'm in simp at line 11. Simp was called from quad simp at line 25. Second, recall that I can look at my variables by typing whos. I see the local variables, that is, the variables defined inside of simp. Suppose I wonder how I got to this point, and I want to look at the variables in the calling function. I can type dbup to return to quad simp without executing any more code. Now I can look at the variables in the workspace belonging to quad simp. I can even go up again, which gets me to the base workspace, that is, the workspace associated with the command window. I can then look at the variables in this workspace. In fact, there's only one. When I'm done looking at variables, I can go back down into quad simp by typing db down, and then I can go down again to get back to simp. Now there's a shortcut in the Matlab editor that allows me to avoid dbstack or dbup or dbdown. It's this drop-down menu here. If I just click on it, I see the traceback listing. And if I click on one of these functions, then I move to the workspace associated with that function. So for instance, now in the base workspace, I can go back here, go back to quad simp. Now I'm in quad simp's workspace, and once more I could get back to simp. And here I'm in simp's workspace. Now let's use the debugger to do some actual debugging. I created a version of quad simp and simp that contains an error. The new code comprises the functions quad simp1 and simp1. So I'm going to try to compute the same integral as before, the integral from 0 to pi over 2 of sine of x, but now with quad simp1. Notice that I'm still paused in the debugger, so I'll type dbcont to finish that execution. I will then type dbclearAll to get rid of the breakpoints I had before. Now I'm going to execute the quad simp command again, except I'm going to call the version called quad simp1. Notice that the code does not seem to stop. I can stop it manually by typing Control-C. For comparison, let's run the correct code. You see the correct code does not take any appreciable time to execute. So there must be an error in quad simp1. I'm going to create a breakpoint and then run the code again. Let's see if we can determine why the code takes so long to execute. I'll step through the code to see what happens. So the first estimate of the integral, which is computed by Simpson's rule, is not too far from the exact value of 1. Let's carry on now. The second value is actually farther away. It's less accurate than the first value. Now let's keep going. Here's the next value computed by Simpson's rule. It's even less accurate. And this continues as I go on. So to try to figure out what's happening, let's step into simp now. So remember, I click on step in to go into that function. Now how should I debug simp1? It's generally true that it's difficult to simply read the code and figure out what's wrong with it. One reason for this is that if you're the person who wrote the code, then you're likely to see what you intended to write instead of what you actually wrote. Since we're pretty sure that the bug is in simp1 and simp1 is not a very long function, I recommend working out a simple example by hand and then stepping through simp1 to see if it's doing the calculation correctly. Before doing this, let's take a look at the code. I have some preliminary error checking, for instance, checking whether a is less than b. and checking if n is actually even as it's supposed to be. Then I have this loop. Each time through the loop, I compute two function values and I add them to the running total. Notice that the loop runs from I equals 1 up to n over 2 minus 1. The simplest case would be n equals 2. In that case, the loop would not execute, and the value would be determined by this single line of code. On the other hand, I'm going to have to use at least n equals 4 to force the loop to execute. So let's first remove all the breakpoints. Let's do dbcont to continue the execution. By the way, there is a shortcut for removing the breakpoints. I can go to this breakpoints pull-down menu and choose clear all. Now let's do the calculation of the same integral with n equals 2. I'm going to do the calculation by hand first. So I choose n equals 2. I compute dx. And now Simpson's rule with n equals 2 would take the form dx over 3 times the value of f at 0 plus 4 times the value of f at the midpoint, which in this case would be pi over 4, plus the value of f at the right endpoint, which is pi over 2. So there's the value that I should get. Let's invoke simp1 directly now to see if that's the value that I get. It is. So the code appears to be correct in the case n equals 2. Now let's try n equals 4. For convenience, let's give a name to the sign functions. I don't have to type quite so much. And then let's type in the formula for Simpson's rule in the case of n equals 4. So I have f of 0, which 0 is a, 4 times f of dx, plus 2 times f of 2 times dx, plus 4 times f of 3 times dx, plus f of b, or f of 4 times dx. That's the value I should get from simp1. What value do I actually get? So let's try it again, but now we're using n equals 4. I don't get the correct value. So this strongly suggests that the problem is in the for loop, the part of the code that does not execute when n equals 2. So we've completed the most difficult part of debugging, which is often called localization, that is, finding which part of the code is at fault. So let's look at simp1. Let's look at the loop. I really have to examine only 2 lines of code. And if I look at them carefully, hopefully you'll see that the mistake is right there. I'm supposed to be multiplying that function value by 2. So let's make that correction. Let's save the code, and let's run it again. And now I get the expected value. Let's go back and run the quad simp1 program again. Now it seems to work fine. I'm going to do one more example of debugging. I have a function that implements Newton's method. I'm going to apply it to this function. The function is f of x equals x cubed minus x minus 1. For the purpose of Newton's method, I have to implement that mathematical function in a Matlab function that computes both f of x and f prime of x. I've stored that Matlab function as f5.m. Now here's how Newton's method works. I'm going to show you the correct version. So I have to pass it the function. I have to pass it a starting point, and I'm going to use x naught equal to 1. I'm going to give a print flag equal to 2, which means I'm going to display a summary of the progress at every iteration. I'm going to choose a small tolerance for the error and even smaller tolerance for the function value. And then I'll use the default value for the maximum number of iterations. Now that's the correct version of Newton. To provide an example for debugging, I introduced an error and created a new version called Newton 2. When I execute Newton 2 on the same problem, I get very different behavior. Now let's go back to the output of Newton, which is displayed here. How do I know that this is working correctly? Well, if I look at the output, I see that in particular the estimated error goes from 1.5 times 10 to the minus 1 to 2.3 times 10 to the minus 2 to 4.8 times 10 to the minus 4, and then 2.2 times 10 to the minus 7, and then 4.4 times 10 to the minus 14. The error is approximately squaring at each step, which is the expected behavior for Newton's method. We see a similar pattern in the values of f, from 10 to the minus 1 to 2 times 10 to the minus 3 to 9 times 10 to the minus 7 to about 2 times 10 to the minus 13. We would then expect to see something on the order of 10 to the minus 25 or 10 to the minus 26. However, here we've reached the limits of finite precision arithmetic. Notice also that I'm printing this convergence ratio. This is the ratio of xk minus 1 divided by xk minus 1 minus xk minus 2 squared. That should converge to a constant if Newton's method is converging at the expected rate. And we see that it appears to do so. It appears to converge to something like negative 9 times 10 to the minus 1. So I have several ways to verify that Newton is behaving as expected. On the other hand, the results for Newton 2 are quite different. The values of f of x don't seem to converge to 0. The estimated error does not seem to be decreasing to 0. And the convergence ratio does not appear to be converging to any constant value. So by every indication, this version of Newton's method is not converging correctly. Let's examine the code using the debugger. So I'll put in a breakpoint. Remember, this is called Newton 2. Then I'll run the code again. Now remember that if dbstop is used to insert a breakpoint in a function, the execution will stop at the first executable statement. Initially, x is 1, as it should be. After I execute this first step, f of x is negative 1 and df of x is 2. I can then calculate what the next value of x ought to be. It should be x minus f of x divided by f prime of x. I should get 1.5. I step past the code that handles the default inputs. I've also got a print statement because I requested printing at every iteration. And then I enter the loop, and here's where the next value of x is computed. It is indeed 1.5 as it's supposed to be. So let's continue to step through the loop. I get the new value of f of x and f prime of x. I check the stopping tests, none of which are satisfied. I prepare for the next iteration. I print the summary as requested. And then I go up to the beginning of the loop again. Here's the calculation of the new value of x. I get 2. Now is that correct? So if I go back to the command window, get x1 equals 1.5. I need to compute the value of f of x1 and f prime of x1. I get these values, and now I can compute the new value of x. Aha, I get 1.3, not 2 as Newton 2 computed. So Newton 2 has computed the wrong value for x. Let's check the computation and see where this came from. X has the value of negative 1.5, as it should. But fx has the value of negative 1. In fact, we see that fx ought to have the value of 0.875. So the value of fx here is incorrect. dfx has value 2. We see that it should have value 5.75. So that's also wrong. So let's look at the code. Here's where the values of f and df were computed. The first time through, I computed these with the input x1, checked the stopping tests, and then copied the values of fx1 and dfx1 to fx and dfx. Hopefully you can see the error, though. At this point, I should have evaluated f at x1, but I mistakenly evaluated it at x. So let's fix that error. Save the file. And let's try it again. Notice that Matlab does object to my changing the file while it's being debugged. But in this case, I do want to exit the debugger and save the changes, so I'll click OK. Back in the command window now, I'll execute Newton 2 again. Notice I made the mistake of not clearing the breakpoints. Now we see that Newton's method behaves as expected. This completes my introduction to the Matlab debugger. If you want more information, I suggest Googling debugging in Matlab.